Myself, I've been in the motor industry for more than, 25 years. Uh, I originally started as a motor designer and moved my way into, you know, all kinds of business opportunities with motors and motor systems, motor assemblies. Then in 2019, we started Sierramotion, and Sierramotion is really focused on customized solutions involving motors. So not only motor components, but motor components built into custom assemblies, such as robot joints and specific actuation for everything from medical devices to satellites to semiconductor machines. There's really three main areas in surgical robotics. There is a surgeon console or some kind of gimbal that the surgeon moves around that initiates motion with the robot tools. There are motors all behind the apparatus that the joysticks, if you will, that the surgeon moves. Those motors are usually there to create some kind of haptic feedback so that the either weightlessness or keep out zones or what have you. So motors are used in the surgeon console. Motors are also used in moving the tools. So as the tools get inserted into the body, each one of those tools has a motor on it, whether it's a gripper or a cauterizer or you're actually doing the operation. Motors move all those tools. And then thirdly, the patient cart robot, depending on the type of robot it is, but there's generally an articulated robot that's next to the patient, and generally that moves into a pose for a specific procedure, and then it might change its pose, but generally it's a robot that you might see in a factory, but it's more specific to the operating room, and it moves into a pose so that then the tools can do what they need to do. Meanwhile, the surgeon's off in a corner in a console, and they're remotely controlling the robot. Three areas: tools, patient cart, and surgical console. So for the joint itself, it always includes a motor of some kind. In some cases, depending on the size and the torque requirements, it can also include a gear system. And that can be a simple planetary gear. It can be something more precise, like a zero backlash gear, depending on which axis it is. And then it includes an encoder. So there's an encoder or some kind of feedback device that allows the control system to run the motor. So you're talking about, a motor, an encoder, possibly a gear. And then in many cases, if you have a gear, there's also an output encoder, because what's happening at the motor is then reduced by the gear ratio. So there's a output encoder usually. Most commonly, those encoders today are absolute encoders. So at the output, you know where you are within one revolution, and at the input, you know where you are within one revolution and can control the motor. Actually, once in a while, you'll also have a torque sensor. Depending on the application, if it's more collaborative, then it's important to sense torque, and so that you don't have any disconnect between what you're asking it to do and what the actual unit is doing. Well, in each of those three different applications, the requirements are different. If you have a surgeon console that you're moving, and you want the surgeon to, all the motion that the surgeon moves and what the surgeon feels when they move the joysticks, it's really important that any torque or force that's created is something that you want to create, not is something that is naturally there. And so in a surgeon console, you want motors that are very smooth operating and have zero cogging. And so the attributes for a surgeon console are, pure torque control, no cogging, no hysteresis, no friction. Basically pure weightlessness, if the feeling has to be pure and smooth. Slotless motors are the most obvious solution there, and then even more important than that is a air core slotless motor where there is no core of iron in the motor, so it's just purely magnets and copper in there. That makes the smoothest motor. So then if we move on to like the tools, because it's a very condensed package and it's essentially guided by the surgeon, the small size and condensed package usually require a gear set. So now you're talking about a motor in a gear. There are smoothness requirements, and because of the size and the integration, a lot of the motors in this that are used in the tools are also slotless because they have a nice form factor and can have a big hole in the center and a very thin radial cross section to the motor so that it fits in nicely when it's nested with other motors. And then you get to the patient cart side where now it's more of a traditional articulated robot, and there it's about torque and holding and positioning. In that case, a motor with a very high motor constant, which is its torque output for the amount divided by the amount of heat that it generates. That's traditionally the motor constant. We use that globally. You're looking for a motor with the highest motor constant so it can give you the most torque in the smallest package. It may be with gears, it may be without gears, but it's generally the highest motor constant. And in that case, it doesn't. Smoothness is taking the second seat to the highest torque output per watt, if you will. Motor integration. So, it's easy to go, off to a supplier or a distributor and buy a motor, and that's traditionally a round thing with a shaft on it, and you put power to it and it turns. So that's your traditional motor. When we're talking about surgical robotics and the kind of applications, we're really taking the motor components, which is a stator and a rotor, essentially the magnetic parts of a traditional motor. We're throwing away the housing because the housing now is an integrated piece of the robot. And then we're adding bearings. We're adding an encoder, as we talked about before. We might be adding gears. We might be adding a brake. We might be adding a torque sensor. So how those things are all integrated is really critical to the function. There's everything that's in there that's creating heat is sharing the same housing. So there's thermal analysis and thermal results of the decisions that you make. There's mechanical accuracy of how everything goes together. You have precision that's required to get the kind of accuracy you want out of your encoder. So you can't have sloppy bearings. You need to have a unique integrated design. And then what's happened traditionally is as these robot joints get designed, there's more and more integration. Like we generally will take the motor and we'll put the brake inside the motor so that the motor and brake don't add additional length every time you add, a component. We'll integrate the encoder with a component-based encoder so that the scale turns with the with the motor rotor, and the sensor is located, uniquely into the housing someplace, so we don't have the traditional gearbox, motor, encoder, brake, all in line, because length is the enemy of mobility in a robot. You can't have motors sticking out because that essentially limits what you can do with the movement. So I think that integration is really a design integration. It's different than just buying a motor off the shelf from a distributor that goes at 3,000 RPM. We're talking about a complete electrical integration, performance integration, mechanical integration, and a thermal integration. So it's all related. Everything you've learned about data sheets and selecting motors, you can basically throw them in the wastebasket, because with a surgical robot and anything medical that's in the operating room where there are patient surface temperature guidelines, depending on how the robot's designed, those the surface temperature guidelines filter back to what kind of heat the system can dissipate, which then filters back to how much heat the motor can generate without exceeding the thermal limit that is no longer an industrial thermal limit. So all motors are rated industrially so that, it goes into some factory, it's not near any people, and basically, a motor manufacturer puts materials in the motor that might be good to 200 C, and then they'll rate the motor at 150 C, and they'll say, well, this is a 1 Newton meter motor at 150 C, and it can go into a 40-degree factory environment, and everything's great, and that's a 1 Newton meter motor. If you take that 1 Newton meter motor and you put it in a surgical robot, it's probably half that amount, because you can't let the motor get to 130 C, because you'll never keep the patient's surface temperature of the robot at 42 or whatever the limits are, for the particular application. So you have to significantly derate the motor. So the data sheet and any torque information that's provided with a motor is subject to be wrong. And so in a surgical robot or any medical device, you really have to re-rate the motor based on the application and induced thermal limits, which reduces the torque. That's why we don't really use, you have to publish torque because everybody does, but we generally use the rated, the motor constant instead of the rated torque. So that is a way to figure out how much torque per square root of watt, the torque output for the amount of heat that the motor can generate, and that's driven then, connected to how much heat the robot can dissipate without getting too hot. The go-to solution usually is an off-the-shelf motor. Okay, let's see if we can get a motor from XYZ company that can provide this torque. And based on what I said 5 minutes ago, none of that's real, because the torque rating for the motor is not rated in a thermal environment that is conducive with the medical devices. The next thing is, usually integration means not duplicating bearings and multiple couplings and all those things that you need to have a motor coupled up to some other set of mechanics. You want to integrate and reduce components and reduce size. You're generally integrating pieces together closer. So an off-the-shelf part doesn't have that. Now, there are some off-the-shelf components you can buy that someone before has designed into some robot for, semiconductor that might work also in a surgical robot. And in that case, there are off-the-shelf components you can get to use in your integration. But again, it's a medical device. So at the end of the day, it's got regulatory controls on it. And there is not one medical device company out there that doesn't understand that if they can't control the design of the robot, they can't continuously build it. So there's a reason to buy custom. And the reason is that if you buy a custom product, you as the customer can control the revision of the product. And so if the supplier can no longer get that bearing or that particular wire, they have to notify the medical device company that they're working with that this is the problem, we need to make a change. And so the change becomes something that's under the control revision of the medical device company. You can't get that with standard off-the-shelf products. If they decide the bearings aren't good, they're going to buy them, they can't get them, they're going to get a different bearing that's the same size from a different place. They just go do that. And you have no idea next time you get the motor that they changed the bearing. And maybe it doesn't matter to the general public, but it matters to the medical device. And if you can't have changes in the product and then have a problem and have the FDA come back and say, well, what was the problem? Well, the bearing changed. Well, how come the bearing changed? It's because the motor manufacturer changed the bearing. Well, why don't you have control over the rev? That doesn't work. So at the end of the day, in a medical device, the custom product, even if it's a standard product with some modifications, it's got a custom part number, it's controlled. The customized solution is the way to go, and that's what most people do. Maybe on the first prototype they buy off the shelf because they can get it quick and make things moving. But at the end of the day, if you want rev control, you need custom. For most cases, engineers do a good job. There's a lot of lessons learned in most companies that by the time something gets truly designed in, enough people have looked at it to understand all of the potential failures or areas for error. But by far the most common thing is misrepresenting. The data sheet for the motor doesn't give you everything that you need. With a medical device or a surgical robotics system, you can't count on the data sheet as, hey, I got a motor that's 1 newton meter, like we said before. I mean, it's 1 newton meter only under the conditions it was tested in, which are not the conditions that the medical device. So they select a product based on a data sheet, and then they realize later that it's too hot. Why is my motor too hot? And now I have to keep reducing the current. Now I can't get the performance. And all of that could have been caught earlier if they recognized that it's an integrated system. There needs to be a thermal model. There needs to be an electrical model. There needs to be it's not like throwing a motor on a conveyor in a factory to move candy bars around it. We're talking about an integrated system. And so the biggest thing is that the motor's selected wrong, or they select a motor because it's small size and it has high torque, and they put it in a surgeon console and it has cogging torque, and every time the surgeon moves the joystick, it feels all this bumpiness that's not really there. And so cogging torque is not specified on most data sheets. So the biggest problem is that the industrial world has created a set of parameters for the motor that, to characterize the motor and make it look good in the setting that it was designed for. And in the surgical robotics setting, most of that goes out the window. Things you really need to know are not on the data sheet. The things on the data sheet are generally optimized for industrial use, where you can handle high temperatures and things, and in the real world you can't. So that is a challenge for the designers, and the mistakes usually are made once or twice, and then they realize that, okay, I need to take more ownership of this. Yes, it's a good motor because it's manufactured by a good company, and it's got a reasonable price and small size. But at the end of the day, you need to know what the motor cogging is. You need to know what the hysteresis of the motor. You need to know the friction in the motor. You need to know, how to rate that motor in the application. And it's really critical that you understand thermally what the thermal paths are, and how many watts of heat flow that you can actually dissipate and still stay within the overall system thermal limit of patient surface temperature, or whatever it is. So Sierramotion was a young company with a lot of engineering capability to help customers engineer solutions around all those things we just talked about. We were growing very, very quickly, gaining some very high-profile customers. And we, as a smaller company, didn't have the global manufacturing presence and the manufacturing capability that other companies did. So there are companies out there with great manufacturing, but they don't have the upfront engineering support. And so we joined Allient because Allient has global manufacturing. They make over 8 million motors a year, and they have factories all over the world, 2,500 people. They know how to manufacture things in volume. And so it's kind of a natural transition, and it put us in a really good position to scale the company. So we can still have the upfront engineering support, design-in support, and we also have the high volume ISO 13885 controls and production in the US, Europe. We have factories all over the place. So it's a great marriage, and it allows us to continue to do what we do, and then give the path to the customer for the volume production in an approved facility.